Hello everyone and welcome. Today we're going to tackle a concept that's, right at the heart of modern AI and data science, Bayesian networks. And the beautiful thing is, they're built on some really simple ideas. So if you've ever wondered how systems can make these smart predictions, even when things are uncertain, well, you're in the right place. We'll start with the absolute basics of probability and build our way up step by step. By the end of this, you'll see not just what they are, but why they are such a brilliant, elegant solution to a very big problem. So, shall we get started?
Okay, so here's our plan for today. Think of it like climbing a ladder, one rung at a time. We'll start with the fundamental rules of probability itself, then we'll learn how to represent uncertainty using something called random variables and distributions. After that, we're going to hit a wall, a really big problem that makes these simple tools kind of difficult to use in the real world. And that's exactly where we'll introduce our hero, the Bayesian network, which is the elegant solution to that very problem.
All right, let's jump into our first section, probabilities basic rules. We're starting at the very beginning. And you might be surprised to learn that the entire massive field of probability is built on just 3 unbelievably simple, intuitive rules. Let's have a look at what they are.
Okay, let's break these down. These are the 3 fundamental axioms of probability. First up, P of A is greater than or equal to 0. All this is saying is that probability cannot be negative. Simple, right? It's either 0 or it's positive. Second, P of omega equals 1. Now this omega symbol here, it just represents every single possible thing that could ever happen. So this rule just says the probability of something happening is 1, or 100%. Makes perfect sense. And third, if you have events that can't happen at the same time, the slide calls them disjoint, the probability of either one of them happening is just their individual probabilities added up. Think about rolling a dice. The chance of getting a 2 or a 3 is just the chance of a 2 plus the chance of a 3. And that's it. Believe it or not, every single rule in probability theory is built from these 3 simple ideas.
Okay, so with those rules in our toolkit, let's move on to section 2, random variables. See, to really work with probability in a useful way, we need to connect real-world outcomes, like it will rain today, or I will roll a 6, to numbers that we can actually do math with. And that is the job of what we call a random variable. Let's make this a bit more concrete. Look at the classroom on the left, right? Each of those students is a possible outcome in our little experiment. Now say we want to talk about their grades. We can create a random variable, let's call it G for grade. You could think of G like a little machine. You put a student in one end, and it gives you their specific grade, A, B, or C, out the other. It's really just a function that maps an outcome, the student, to a value, which is the grade.
And here we have the formal definition, which this slide shows perfectly. The sample space on the left, that's our whole group of students. The random variable in the middle, well, that's our function, our rule. And what does it do? It maps each one of those students to a specific value, A, B, or C. It's simply a nice, structured way to put a label on uncertain outcomes.
So now we have a way to define outcomes, but what's the next logical question? Well, how likely is each outcome? What's the chance of a student getting an A versus a C? To answer that, we move into section 3, probability distributions.
Now things get really interesting when we start combining variables. Here we're looking at 2 of them, G for grade and I for intelligence. This table you see here is called a joint distribution. I want you to think of it as the complete rule book for how these 2 variables behave together. It gives us the probability for every single possible combination. Let's just look at the first row. The probability of a student having high intelligence and getting a grade A is 0.3, or 30%. The second row tells us the probability of low intelligence and a grade A is 0.1. This one table contains the entire story of their relationship.
But our joint table is very specific. What if we have a much simpler question, like the slide is asking? What's the overall probability of just getting a grade A? Regardless of intelligence. We don't care if the student has high or low intelligence, we just want to know the probability that their grade is A. So how do we figure that out from the table we just saw?
Well, the answer is a process with a fancy-sounding name, marginalization. The name might sound a bit technical, but the idea is actually very simple. To find the total probability for one variable, like getting a grade A, we just have to think about all the ways it can happen. It can happen if the student has high intelligence, and it can happen if the student has low intelligence. So, as the slide shows, we just sum up the probabilities across the variable we want to ignore. We are marginalizing out the intelligence variable to focus only on the grade.
Let's just trace the steps here on the slide using our example.
We want the probability of grade equals A. So, step 1, isolate. We go back to our joint table and we find every single row where the grade is A. There are two of them, the one with high intelligence and the one with low intelligence. Right? Okay, step 2, sum. We take the probabilities from those two rows, which were 0.3 and 0.1, and we just add them together. And step 3, result. The sum is 0.4. That's it. That's our marginal probability. The overall chance of any student getting a grade A is 40%.
Now, for another really crucial idea, conditional probability. This is all about updating what we believe based on new information. Now look at these two tables. The top one shows the probability of a grade given we already know the student's intelligence is high. Here, the chance of an A is pretty good, 0.6. Now look at the bottom table. This is for when we know the intelligence is low. Suddenly, the chance of getting an A drops all the way to 0.3. So the condition, the extra information we are given, completely changes the landscape of probabilities. This is really the core of how we reason when things are uncertain.
Okay, so these tools, joint and conditional distributions, they work great for two variables, but here's the catch. Real-world problems are not that simple. They have tens or hundreds or even thousands of variables all interacting with each other. As we start section 4, we're going to see why our simple joint distribution table approach completely, utterly breaks down. We're about to hit a massive wall.
Let's just take a real-world example, right? Imagine an oil company is trying to predict the chance of finding oil somewhere. Now, this doesn't depend on one or two things. It depends on many different factors, as you see in the diagram: salinity, water pressure, depth, temperature, and so on and so on. To perfectly model this situation, they would need to build one giant joint distribution table that lists out the probability for every single combination of all these different factors. And here is the heart of the problem. Let's say we have n variables. And just to keep it simple, let's say each one can only have two states, like high or low, yes or no. The number of entries we would need in our joint probability table is 2 to the power of n minus 1. Now, the key takeaway here is not the formula itself, it's the n in the exponent. This means the size of our table doesn't grow nicely and linearly, it grows exponentially. And that, my friends, is a complete disaster. This exponential growth leads to 3 impossible challenges, which the slide calls computational, cognitive, and statistical. Let's just break that down into simple terms. Computationally, a table with just 30 binary variables has over 1 billion rows. You can't even store that on a computer easily. Cognitively, you can't ask a human expert to sit and fill out a table with 1 billion rows. It's just impossible for a person to think about that many combinations. And statistically, to learn these values from data, you would need a mind-boggling amount of data to have seen every single scenario. So, we are completely stuck. So, the joint distribution, which seemed so powerful just a few minutes ago, is actually a dead end for real problems. It's perfect in theory, but impossible in practice. And this brings us to section 5, and the brilliant, brilliant solution to this entire mess, the Bayesian network. Okay, so the core idea is to completely shift our thinking from a massive table to a smart, simple graph. As you can see, each variable is now a node, a little circle, and the arrows between them represent dependencies. But here is the absolutely crucial part. We only draw an arrow if one variable directly causes or directly influences another one. We don't just draw arrows between everything. We capture the actual structure of the problem. So for instance, intelligence directly affects a student's grade. This sparse, graphical way of looking at things is the key insight.
All right, enough theory. Let's put this all together and see one of these networks in action. In this final section, we're going to build a complete model and see exactly how it solves all those problems we just talked about.
We're back with our student example, but now it's a full-fledged network. Let's just trace the logic of the arrows for a second. Notice that both difficulty and intelligence are pointing to grade. This just means the grade depends on both how hard the class is and how smart the student is. Makes sense. Intelligence also points to SAT, which also makes sense. And finally, grade points to letter, meaning the grade is what determines the quality of the recommendation letter. See, this simple graph tells a complete causal story.
And this is the breakthrough. Remember that massive, impossible joint table? It's gone. Instead, each node now has its own small, manageable, local probability table. Let's just zoom in on grade. Its table only depends on its direct parents in the graph, difficulty, and intelligence. It doesn't care about SAT or letter directly at all. Every single node just has a compact little conditional probability table, or CPT,
that tells us the influence of its parents. This is infinitely more manageable.
So, how do we calculate the probability of a full scenario now that we don't have the big table anymore? Well, this is the elegant part. As the formula at the top shows, the joint probability of all 5 variables is simply the product of the individual conditional probabilities. Let's walk through the example here. We want to find the probability of this exact outcome: I equals 1, D equals 0, G equals B, S equals 1, and L equals 0. We just go to each little table and pull out the right number. From the I table, PI equals 1 is 0.3. From the D table, PD equals 0 is 0.6. From the G table, we have to look up the probability of grade equals B, given that I equals 1 and D equals 0, which is 0.08. We do this for every variable, and we just multiply them all together as we go. We've replaced one giant impossible table lookup with a few simple lookups and a multiplication. That is the power of this structure.
And so we arrive at our final, formal definition. A Bayesian network is really made of 2 key ingredients. First, there's a structure, a directed acyclic graph. Directed just means the arrows have a one-way direction, and acyclic means you can't go around in a circle. This graph shows us what depends on what. And second, there are the parameters. For each and every node, there's a conditional probability distribution, one of those little tables that tells us how much it depends on its parents. And together, these 2 parts give us a compact, a powerful, and very intuitive way to model a complex and uncertain world.
So we've gone all the way from the 3 simple rules of probability to building a complete, powerful model. Now, to leave you with the final thought, how could you apply this? Think about your daily commute to work or to college. What are the variables? You have weather, traffic, the time of day, maybe whether your alarm went off on time. What causes what? Does the weather directly affect the traffic? Does the time of day affect which bus you take? Try to just sketch out the graph. It's really the best way to understand the power of thinking in networks. Thank you for joining this explainer.